Okay. Welcome everybody to this session. We're going to have several papers on music generation, starting with a paper on variational autoencoder for music generation controlled by tonal tension by Rui Guo, Eva Simpson, Tor Magnusson, and Doreen Hermans. And we pass it over to Rui now.
Thank you, David. Can I share the screen? Hello, I'm Rui Guo. Today, I'd like to talk our research to use a variational autoencoder for music generation controlled by tonal tension. This is a joint work between University of Sussex and the Singapore University of Technology and Design. Music is one source of emotion for film and game music. When people propose some generative music algorithm for film or game, they usually resort to some other factors such as tension, rhythm, timbre, and dynamics. Because a direct control of emotion is very hard, so people must find some other way to control the emotional correlated factors. So in this work, we try to use tension to generate some music and control the tension in the generated music. How do people use the AI music generation is a big question. The AI music generation system can have different forms and different skills. One type of generation system is to generate full song, but with relatively less control. For example, music transformer can generate accompaniment given the melody. And the music Autobot can generate the harmonization given the melody or generate a chord, generate the melody given the chord. Other types of generation systems generate short music, such as 4-bar or 2-bar long, but they have more attribute control. For example, pitch rhythm or chord and texture. According to a recent survey, it is shown that the decomposable and context-aware system, which is to build music from phrases to phrases, is more preferable by the musicians or the amateur users. And by this way, the phrases can be annulled with some attribute, such as tension. But the current generation system, they usually ask the user to have some music background. So we propose this system is to ease the user without any music knowledge, so they can still generate some meaningful music. The tension we used here is tonal tension. It is just related to pitch. And here we do not consider the pitch registers, for example, the higher pitch or lower pitch in this research. So the tension only comes from the relation of the intervals in the music. What the tension brings is the dissonance, but the dissonance can build on the expectation and let the listeners give some waiting for the resolution. So actually it announces different phrases of music. The tonal tension space we use here is called a spiral array space. It's a three-dimensional space, and each note is mapped to a three-dimensional space. And in that space, it has some good attribute, which is in accordance with people's perceiving of the music. For example, the perfect fifth has a closest distance in that three-dimensional space. And the major interval distance is closer than the minor interval distance. So actually, it reflects what people perceive in their normal music listening experience. And based on that work, Doreen Hermans and Alan Chu proposed several other tension measures. Two of them is called tensile strain, and the other is called cloud diameter. Tensile strain is a weighted distance of the note position in that space, and note is the distance between the note position and the key position in that space and in a short time window. And for this figure, we can see that the first chord is C major and the second chord is C sharp major. If we assume the music is in key of C major, the C sharp major has a larger tensile strain because this chord is not in key with the C major. The other measures used here is called cloud diameter. It is the largest distance between two notes in a time window. In this figure, we can see that the second chord is the C diminished chord. It has a C diminished, diminished fifth interval, and that interval has a larger distance than all the other intervals in the first C major chord. They are two complementary tonal tension measures because the first tensile strain considers all notes in the time window, and it is a weighted average of the distance between the note position to the key position, but the cloud diameter only considers the largest distance between a pair of notes in a specific time window. So that's why we choose those two measures, and we want to use them to control different aspects of music. The model used here is called a variational autoencoder model. That model usually reconstructs the input. Here, it usually just reconstructs the input, but here we add several other constraints here. We add another two output. One is tensile strain, the other is cloud diameter. So given the input, the model tries to predict the tension inside the input. So the benefits of that model is to incorporate the tension into this model, and then let this model to predict the tension just given the music. The input data format used here is the piano roll consisting two monophonic tracks. One is melody, one is bass. We choose two tracks to ease the generation, but also let the tension, because we need at least two tracks. For example, if they are all monophonic, and then it can generate some more meaningful tension here. And each track is represented by pitch and rhythm feature. All songs are pre-processed to 4-bar long, and it is cut to 4-bar long snippets, and the 16th note is the shortest time step used here. And all songs are changed to C major or A minor, and we use the log dataset for building the training dataset. And also in the pre-processing, we do some track separation to extract the melody and the bass track, and use the MIDI minor to calculate the tensile strain and the diameter in all the data in the data set to let the model to learn to predict the tension here. After the model is trained, we need to find some interesting tension feature vectors to manipulate. So here we use two types of tension feature vectors. One is called the directional change. The other is called the level change. The directional change is a gradual change. Here you can see from the intro to the chorus, the tension goes up, but for inside different sessions here, in the intro and the chorus, they have different tension levels. So that's why we chose those two type of tension feature vectors. We want to control one type is to make the tension from low to high, but for the other type, we just want to for the whole session the tension is high or low. And to find those two types of feature vectors, we need to first add labels to our tension calculation. So we add two kinds of labels. One is up or down here. For example, up is like this shape and down is like this shape. And this type of tension is used to extract the directional tension feature vector. And the other type is high or low. So that is we just compare to some thresholds to find those two types. And after we find the different classes of tension, we iterate on two classes, for example, up and down, until the difference between the mean of all those two classes stops to change. And in this way, we can find several tension vectors. One is directional change, the other is a level change. After they are extracted, we need to evaluate if they really works or not. For example, here is the result about tension direction change, tension direction feature vectors. The method we evaluate is first, we want to find the tensile strain. For example, here we use a tensile strain upward ratio. The upward ratio is the tension up. If the tension has a upward shape in the second two bars, and we also calculate the tension upward ratio, upward shape, if it is upward or downward in the first two bars, and we have the ratio between the second two bar and the first two bars. Because it is a gradual change. And we can see that if a large weight vector is added to the latent space Z, the generated tensile strain will have a higher upward ratio here. And if it is a minus weighted tensile strain, it will have a very low upward ratio. And we also compare the pitch and the rhythm F-score, the reconstructed accuracy here. We can see that the pitch accuracy is lower than the rhythm F-score. So that shows that the pitch is affected more than the rhythm. And it's the same for the cloud diameter. And we also like to see if one type of change affects the other type of tension feature vector. We can see here the tensile strain. If we change the tensile strain, the cloud diameter upward ratio doesn't change a lot. And the same for the reverse. And here is the tension direction change and the tension level change interaction. So one type of change only affects itself. It doesn't affect the others. The last type of experiment we like to find is that if it changes the pitch ratio of output music. The original pitch ratio is nearly the same between the first two bar and the second two bar. And if we add some tension direction feature vector to the latent space, we can see that the C pitch and the G pitch goes down a lot in the second two bars, but all the other pitch goes up. And for the level change, we can see that the C sharp and the F sharp pitch ratio goes up a lot. And actually other tension shape change is possible. If we can define the arbitrary shape, for example, we can define the up and down shape, and the result actually validates this kind of research. Now it's a demo time, and here is original music. And we add some tensile string direction going up vector into the latent space, and it's generated music here. This is a figure to show the tensile string in the output music. And if we add a minus weighted tensile string direction vector, the output is here. For the time constraint, I will not show the other examples. And we have a Colab notebook for the user to use this algorithm. And first people to install the packages and load the feature vector, and I will skip those steps. And user can select example here or upload their own MIDI. Here, I just use a preset example 4, and after those cells are run, so the original music is here, but I like to play here. This is a concatenated forward music, which is used as the start point of this algorithm. I will not play the rest. And here, the user can select a few tension feature vectors if they want to include in their experiment or not. And they can select some other, for example, the factor, the largest factor, the range of factor added to tensile string and to the diameter feature vector here. And after this cell is run, the user run this, the result is here. And here in this example, it just add the tensile string change to the model. So for the first two bar it goes up, and the next four bar it goes down. So it has some increase and decrease of the tension. So it's the preset here. Okay, I will not demonstrate the rest of this notebook. Please have a look if you have interest. So conclusion, this variational autoencoder model can change the input music and sampled music tension, direction, or level. Although it is a fireball model, it can be applied iteratively to every 4-bar, or it can generate variation from a first 4-bar music seed. The user don't need to have the music knowledge to use it. For example, they don't need to have the harmony or other music knowledge. Other tension measures are to be exploited, such as rhythm, dynamics, and timbre, to control the music generation in the near future. Thank you.
Thank you, Rui.
Thank you.
As far as is Bob there? I can't see any questions in the.
I'm here.
Okay. I can't see any questions in the Slack anywhere. So maybe I can kick off. Oh, here we are. Do we have some here? Okay, there's one here from Oded. In describing the motivation, you said that the system will enable people with less musical knowledge to compose meaningful music. In what sense is choosing some parameter transformation of uploaded MIDI, of an uploaded MIDI sample, a meaningful compositional act?
Here, actually, from our experiment, we can see that the tensile string direction change is more related to the harmony progression, and the diameter change is more related to add some notes, but it's with higher tension in the current generation, but it doesn't relate much to the total harmony progression. So actually, we have a number of feature vectors now. For example, the tensile string direction, diameter direction, and the level changes, and we also have an up-down tensile string up-down shape. So the user actually it's up to their exploration of this model. They can choose if they would like to use this or that. to generate the music, but actually it's just absolutely up to the user for themselves to explore this model if they think it is more meaningful to use one or the others.
Okay, thank you. Are there any other questions? Here's one from Zeng. I noticed that the rhythm complexity changes for the generated music. Is it a coincidence, or are you encoding rhythmic dissonance in your tension mechanism?
This is a good question. Actually, at first we don't like to we expect the rhythm shouldn't change much in the generative model, but later we find out the rhythm will be affected. Actually, it cannot be kept intact because here you can now you can see, if you can still see my screen, that here the rhythm F score change here is like that. It's relatively lower than the pitch accuracy change, but it's definitely changed. So the reason for that is that, for example, if we change the cloud diameter, it will definitely change some of the rhythm because it is one way to lower the cloud diameter if there are less notes. If there are less notes in the time window, the cloud diameter will definitely be it has higher probability to be smaller than it has more nodes, because more node has more probability to have a higher cloud diameter because it just compare parallel nodes distance, but it has less nodes. It has higher probability to have a less rhythm, less cloud diameter. So it is a side effect actually of the tension definitions here. So actually, we can try some method to for example, we can to just change just the pitch or just the rhythm. But if we change the tension measures here, it absolutely will affect to some degree of the music output. But sometimes I think the rhythm change is acceptable, because if the rhythm is exactly the same as the input, maybe the music doesn't sound very interesting. But we would like to see if there are better ways to control this model.
Another question from Robin. How much empirical data is there in support of your model of tension compared to others? And perhaps I could just add to that. What are your plans to evaluate whether or not your model is having an effect on the actual input examples you're producing that is perceptually relevant?
Yeah, actually, we have made a user survey, and but at this time, there is still not enough feedback. So actually, we'd like to use a user survey to see if this model really works or not. And actually, we explore the pitch ratio change in the output. So we can see that it has some higher pitch ratio of the notes with higher dissonance, but we still do not have a very rigid evaluation of this model. And another good idea is that I up to now I don't know how to do it, but if we have the Colab notebook there, and to see at the same time if the user uses Colab notebook, can I get some feedback from their usage? But I don't know how to do that at this stage, so that is to be explored later.
And maybe just one other, back to Robin's question, because you kind of answered my question, but you didn't really answer Robin's question about how much empirical data there is in support of your model compared to other models. I mean, why this model of tonal tension rather than another one?
Oh, okay. So yeah, I think this model of tonal tension is, we choose two complementary tension measures here, and it is easy to control that. But there are actually lots of other tension controlled music generation, just like we see yesterday. But we don't see that there is enough outcomes, or it is where it is open source or because we cannot get enough data to really do that kind of evaluation. And it's a good question. If we can, yeah, I think that is to be explored in the future. If we can get enough output from their model and generate enough outputs to compare.
Okay, thank you, Rui.
Thank you very much.
Yep, thank you. We're now going to move on to Zheng Ren, who will give us a video of a talk on style composition with an evolutionary algorithm. And Bob has gone. Zheng, you wanted to oh, here he is, he's back.
Yes, so I will share my screen and then the video. You can see my screen?
I can see your screen.
The video is, where was that video?
It's, I can put the link here in the Zoom chat.
Yes, please do.
Imagine yourself working on a piece of music, and you may say to yourself, I want the music to sound like your albums.
I have to share the
Somebody's
audio.
creating a lot of noise. I think it might, I don't know who it is, but if you could just mute if you're not speaking. Thank you.
To turn a ringtone into a field, connect two phrases. Imagine yourself working on a piece of music, and you may say to yourself, I want the music to sound like Bill Evans. To turn a ringtone into a field, connect two phrases. Modulate from F to E in 4 bars. To use colorful chord extensions if you're into jazz. We note that we want better control over the generated music, and wouldn't it be nice if we have a powerful, general-purpose music generation system? And this is where my research started. One general way to exert our control is by encoding what we want into an objective function. This objective function could be human rating, handcrafted rules, or even neural network. Suppose that we have this function at our disposal. The core question then becomes, given any music evaluation scheme, how do we generate music accordingly? The evaluation could be based on some notion of similarity, based on rules, or interactive rating. And the generated process could be sequential or an optimization process. In this paper, the proposed algorithm generates music by keep modifying a given piece of music in the direction of maximizing a given fitness function. Now let's focus on these two crucial components, fitness function and optimization algorithm. The fitness function can be single-valued or multi-valued, and depending on which, their optimization have very different behaviors. In this paper, we will use a single-valued function for simplicity. Now let's take a look at some examples of musical objectives. In the demonstration in this paper, we're trying to build a 18th century first species counterpoint. So, the fitness are developed into 2 parts, melody fitness and counterpoint fitness. The melody fitness, as the name suggests, only evaluates a single melody. The fitness has 3 tiers concerning hard rules, local shape, and global shape. And the counterpoint fitness use this melody fitness in its sub-evaluation. Notice on tier 2, we have outer voices evaluation and inner voice evaluation on tier 3. Notice that the sub-evaluations related to harmonies are mostly expressed in terms of intervals instead of chord tones. and this is an intentional choice to see if simple harmonic rules can be expressed as the result of contrapuntal rules. We saw that there are many objectives we want the model to achieve simultaneously. So a natural question is, how do we combine them into one function? Many of the previous works using evolutionary algorithm to generate music use a linear combination of sub-evaluations. This is easy to compute, however, not very easy to control and tune. One of the core problems is the difficulty to control trade-offs among sub-evaluations. Suppose we have an objective y, which we want the algorithm to go for it, but only when objective x is met. In a linear combination setting, we will have no way to specify that conditional preference, no matter how we tune the weights. To cope with this, we could start by using a tier structure. That is to only consider higher tier reward when lower tier is satisfied. Although this made it easy to express conditional preferences, it made it really hard to optimize. Since now the model don't get any information about high tier fitness landscape when it is at lower tier. And this opens up the risk for the model to not be able to plan ahead and then be stuck at local maximum. For example, suppose our fitness function puts general contour evaluation at the highest tier, and we all know that having a nice contour requires a lot of planning, and that's why human composers often plan ahead on the shape of the piece. From the model's perspective, it does not get any incentive to make the music contours better when there are more fundamental objectives to be satisfied. And thus, it might be too late when the model sends high tier rewards and be trapped at local maximum. To deal with this problem, I propose a smooth linear combination design. We see that instead of each tier activates on a binary manner, now all the tiers are activated in a smooth manner, and this gives the model ability to sense high tier reward while it is still in lower tiers. And this is the corresponding mathematical formulation. Notice that in the middle, the tiered linear combination is achieved by applying a diagonal matrix, which functions as a pointwise multiplication. The ti's are either 0 or 1, depending on whether a previous tier satisfaction had met to a certain threshold, which is represented by Si. And the only difference between the tier linear combination and the smooth tier linear combination is the middle function highlighted in blue. In a tier linear combination, that function is a unit step function, while in the latter, it is a smooth approximation of the unit step function. Now we dive into more detail on what we mean by a smooth approximation of the unit step function. The function of our interest is notated by sigma, highlighted in blue. The sigma here does not refer to the logistic function, so it's just a notation coincidence. And on the right, we can see a family of smooth functions sigma w, having various shapes, and the only difference is their behavior from -1 to 0. This is the range that represents how far away the previous tier performance from the desired thresholds, or distance to target satisfaction threshold. The parameter w is changeable, depending on how you like your activation to smoothly transit from 0 to 1. The very detail of how the sigma w is constructed can be found in the appendix of the paper. Notice that using this sigma instead of the unit step function encourages the model to not focus so much on high tier at the beginning, but gradually shifting its attention to high tier objectives as low tier ones are met. Usually this fitness function can be very hard to optimize, often non-differentiable or not even continuous, and that is why I turn my head to heuristics like evolutionary algorithm. By the way, there's no reason why we should restrict it to evolutionary algorithm. I use it simply because I feel it's easier to control the local search behavior by designing appropriate mutations on crossover. In a nutshell, evolutionary algorithm is a kind of random search optimizations. The unique point is that they use natural selection to choose candidate solutions and use mutations and crossover to sample new candidates. So the evolutionary algorithm had three core components: population, fitness function, and variation operators. The population is a collection of potential solutions to be sampled. The fitness function is to evaluate the individual population. And the variation operators is to control the change of distribution of candidate solutions. And before we jump right into the detail of variation operator designs, let's have a look at the music encoding scheme. Instead of encoding music as a sequence of events, we use a multidimensional array to capture the rhythmic hierarchical structure of music. Let's have a look at this example. This array has a dimension of 4 by 3 by 3 by 2. The 4 represents there are 4 voices. The 3 represent there are 3 bars. And the second 3 represent that there are 3 beats in a bar. And the final 2 represent that there are 2 divisions in a beat. So you can see this rhythmic hierarchy can be naturally encoded by the shape of the NumPy array. Each entry of the array encodes a general note object, which in addition to pitch can also represent rest and time note. Pitch is represented by integer, rest is represented by dot, and time note is represented by a star. The versatility of NumPy array in computation makes it really easy to manipulate the encoded music. We can choose part of the music by slicing or masking. We can get the core sequence by reshaping and transposing. It also makes it really easy to parallelize computations when implementing our fitness function. And if you want, you can use a music template to constrain the piece. You may want to only allow a certain section to be changeable. You may want to fix the duration of notes in a particular location. Those operations can be very easily implemented by NumPy array masking. We will see more applications of this music template later, together with the generated result. With this music encoding in mind, we can start to talk about the variation operators in this paper. The purpose of variation operators is to efficiently traverse the fitness landscape, which is not very easy. The notion of neighborhood in the musical sense does not come naturally by Euclidean metric. For example, by Euclidean metric, moving the whole voice by an octave is a huge change, and thus would rarely be sampled in a traditional way. However, musically, we don't see it as dramatic as just adding half-step random shift to the whole voice, which will create a lot of dissonance and thus induce a large change in the music quality. So the question arises, how do we incorporate meaningful music operations and also encode them in a systematic way? One thing that we want to have is pitch shift, and this is the most canonical motion to fix a wrong note. But the unique thing about this encoding enables us to make pitch shift hierarchical, performing it on beat level, measure level, and voice level. Another thing we want is a swapping motion. This can be very helpful in permutation-related tasks, especially chord voicings and voice leadings. Again, we can make this hierarchical. On the right, there are 3 examples of this swapping operation, performed in different ways. All the 3 examples perform swapping on beat level, but with respect to different parents. The top swapping happened within a measure. The middle happened in adjacent measure. The bottom happened in adjacent voices, which is equivalent to vertical swapping. The crossover design is very simple. It input 2 pieces, exchange the same part of piece, and output the resulting 2 pieces. It could be exchanging the 3rd measure or exchanging the 1st note. Just by using this simple but hierarchical operator, the number of operations needed to fix a small music problem reduced dramatically comparing to non-hierarchical counterpart. The sampling of the locations to perform the operations are guided by an attention mechanism, which will be introduced in the next slide. To test this algorithm, I built a simple optimization interface for the user. On the top left, we have a snapshot of the best music candidates in the population. The graph is similar to a media plot. The y-axis represents pitch, and the x-axis represents bar number. Each color line represents a voice, and each dot is an 8 note, so a quarter is plotted as 2 8 notes. On the top right, we have an interactive attention plot. Attention is a hyperparameter that governs the mutations of crossover. It basically tells the population to only perform changes on a specific region. The user can click on the cross to specify where the population should focus on in the piece. The purple dots represent the distribution of attention in the spatial region of the music. If the user don't specify the attention will change dynamically on its own. In fact, in this algorithm, the behavior of attention assignment is modeled as a co-evolution process. Attention has its own population and evolution process, and its fitness is determined by their likelihood to lead to better fitness improvement of the music population. On the left bottom, we have an evaluation plot. The user can see in real time how the current best candidate perform in each subcategories of the fitness function. With this interface, we basically turn the human-computer composition process into a stochastic game, where while we are looking at the piece and the evaluation, we assign the attention to guide the music evolution. This observation and action cycle could give room to future expansion with reinforcement learning, allow some optimization experience to be passed down. Here are some examples of the generated music. Depending on the music template, the user can specify fixed notes and free to modify notes in the piece of music. The orange notes are modifiable by the algorithm, while the black notes are constrained. This particular example is where everything is modifiable. This have some constraints. This also, as well as these two. One very interesting point of the music is that we see triads automatically emerges just based on the interval-wise constraint. This is consistent with music theory and the formation of triads based on maximizing contrapuntal consonants. The model generally copes with avoiding parallel octaves or fifths fairly well, but it has some unnecessary weird jumps from time to time. The abundance of first inversion chords is also a surprise, and it has something to do with the way some specific sub-evaluation regarding interval preferences are encoded. There are several other weird spots, and I think it's a reflection of not including some important objectives in the fitness function. A more careful refinement of the sub-evaluation could be very helpful to bring this project further. There are many directions this project can be extended, including even better hierarchical encodings using tree structures induced by some music reduction process. Another important work is to build a library of fitness evaluation. It will first include a collection of useful and customizable evaluations, basically put elementary music theory in concrete terms. I hope this collection gets expanded with the help of musicians, musicologists, and generally everyone else who wants to contribute music domain knowledge. For the application of this research, the first and what interests me the most is to use it in the study of music itself, including music theory, musicology, and music education. We can use it to simulate the musical result of theory about how music works. Secondly, we can use it as a composition tool. This can compose without prior examples, but we need to make clear about what we want in terms of musical objectives. And ultimately, I hope this can contribute to the building of more interpretable music composition AI, establishing a pathway between analysis and composing actions. And finally, I want to thank Professor Panagiotis Mavromatis and Professor Brian McPhee for their valuable suggestions on this research project. I also want to thank the 3 anonymous reviewers for their time spent to provide feedback on this paper. Thank you.
Thank you, Zheng. Are there any questions? If so, then please write them in the appropriate. Here we are. So we've got one from Robin. Are your rules more about making good things happen or stopping bad things from happening?
Yes, and I think that is a pretty good question. So the question is about promoting a reward or penalties. So in my model, we mostly used a reward mechanism, and some of the fitness function also induce some penalties on the qualities that we don't desire for the music.
Okay, thank you. Okay, I have another question while other people are thinking about what questions to ask. Have you tried it on some other musical styles? Have you tried it using the same framework on other musical styles where perhaps the style is not so clearly governed by rules?
Mm-hmm. So I'm thinking if we want to generate a music where styles are not very clearly explicitly expressed as rules, we can replace that fitness function by some neural networks. Actually, we can train some evaluators and use that as a fitness function.
Yeah, what about if those other styles are characterized maybe by a large scale structure that is perhaps hard to express with rules? How do you attack that problem?
Yes, in the future, I want to gradually expand the fitness sub-evaluations, and I'm attempting to actually encode those very complex rules from simple rules.
Okay. I see Robert asked a question here. Well, it's the first one is the same. How might, excuse me, how might this approach be expanded to other styles? We talked about that. It says, have you tested what happens when you give a fixed part that is not part of the style that's been learned? In this case, 18th century tonal counterpoint.
So you can specify fixed parts by using a music template. And after you specify that part will never change. And the model will try to maximize the fitness, meaning that it will try to do everything it can to the other part of the music to make it style consistent.
Okay, thank you. Another question from Robin. Music in the style you work with makes use of repetition. How does your system deal with that? Or is that also a future work? So I think what he's asking is that, okay, in the music that you're trying to model here, there is there's made use of repetition. There are parts of the piece that are repeated and maybe even repeated and transformed, but they bear, explicit relationships with other parts of the piece. How does your system deal with that kind of structural constraint?
Mm-hmm. So currently, the fitness has no don't have a lot of constraints on the repetition. And if you saw repetition in the music, it is totally a coincidence. And if you want to specify how many repetition you want, you can encode that into a fitness function.
Okay, thank you.
Mm-hmm.
Are there any other questions? Do we have time for one more? I think that's about it. So we'll thank Zeng again. Thank you very much, Zeng.
Thank you.
Thank you. Our next presenter is Ray Worley and Robin Laney, who will be talking about generating subjects for pieces in the style of Bach's two-part inventions. So Ray, I guess you should share your screen.
Right, good morning.
Good morning. So,
okay,
over to you.
Thank you. Good morning. My name is Ray Worley, and I shall be talking about generating subjects for pieces in the style of Bach's two-part inventions. Our ultimate goal is to develop software which will allow users to guide the process of generating music in the style of Bach's two-part inventions according to their preferences. Our paper describes how to begin the compositional process by automatically generating plausible musical subjects. In particular, we investigate the usefulness of information theoretic measures as ways of filtering out unsuitable subjects. We use random sampling of statistical models to generate musical motifs that may be considered as subjects for pieces in the required style. The models are constructed by machine learning from excerpts of the 15 two-part inventions. The machine learning employs multiple viewpoint systems. Viewpoints may be basic, such as note duration and pitch, derived, such as interval, test, such as Boolean valued tactus, which is true on main beats in a bar, linked, which model tuples of values from two viewpoints, and threaded, such as pitch threaded tactus, which is defined only at positions where tactus is true. So this is able to model longer term dependencies. Viewpoint models are variable order n-gram models with a defined maximum context size. These use prediction by partial match to construct prediction probability distributions. These distributions are then combined to produce an overall distribution over the duration or pitch alphabet, whichever attribute is being generated at the time. Viewpoints were automatically selected for duration and pitch predicting systems on the basis of a leave one out cross-validation of the corpus, where the aim was to minimize cross-entropy. I shall often refer to two information theoretic measures during the course of this presentation. The information content of a note is minus log2 of its probability. The mean information content of a sequence of notes is the mean of the information contents of all those notes. As the sequence length tends to infinity, mean information content tends to cross-entropy. Random sampling can be modified by introducing probability thresholds. During sampling, note attributes are not generated if they have a probability lower than a specified fraction of the highest probability in a distribution. For example, probability threshold 0.1 times highest probability 0.3 equals 0.03. So all predictions with a probability below 0.03 are ignored. As a starting point, 16 7-note motifs were generated using random sampling. That is, with a probability threshold of 0. We forced them to begin on the second semiquaver of the bar, assuming C major and common time, for direct comparison with the 7-note subject of invention 1. They were all different, with mean information content ranging from 2.83 to 6.09 bits per note. Such large values indicate a tendency towards disorder, and indeed there were many inappropriate chromatically altered notes and large intervals, as we can see from motifs A and B. Random sampling can be modified by the use of probability thresholds, as I mentioned earlier, to generate a greater proportion of suitable subjects. 16 motifs were generated for each of the probability thresholds 1, 0.9, 0.8, 0.7, and 0.6. In all other respects, generation was the same as for the initial 16. We can see that the mean information content is much lower than the 2.83 to 6.09 bits per note range on the previous slide. The motifs are well organized, but not many distinct motifs are generated. In fact, for thresholds of 0.8 and above, only one motif is generated in 16 runs. This is motif C, which is the same as the subject in invention 1. For thresholds of 0.7 and 0.6, there are 4 and 9 distinct motifs, respectively. Motif D has the highest mean information content. We need a compromise such that a large proportion of inappropriate motifs are filtered out, while still allowing a large variety of motifs to be generated. Thresholds of 0.1 and 0.3 for duration and pitch respectively is a reasonable compromise. 48 motifs were generated in this way, with mean information content from 1.54 to 3.46 bits per note. Some are not suitable as subjects, though. For example, motif E contains a note not in the specified key. Motif F has an uncharacteristic rhythmic structure, and motif G is excessively repetitive. We therefore investigated ways of further filtering out unsuitable motifs, focusing on pitch-related issues. High information content H can possibly identify inappropriate pitches in motifs. The first appearance of a subject is usually solidly within the key of the piece, so notes that are not within the key can be perceived as surprising. The higher the information content, the lower the probability. So high H indicates surprise or unexpectedness. We generated 8 10-note motifs in B minor and 6/8 time, starting on the first beat of the bar. To begin with, H was calculated using combined probability distributions for the prediction of pitch. In motif H, an acceptable F sharp has the highest information content, whereas the unacceptable D sharp has a much lower one. This is not what we want. On the other hand, the D sharp in motif I is assigned the highest value, as we might have hoped. Amongst the motifs with an acceptable pitch structure, the highest H is 3.96. This is associated with the A sharp in motif J. Unfortunately, this value is higher than the H assigned to the unacceptable D sharp in motif I. It's clear then that information contents based on combined distributions are not able to identify unsuitable notes. Next, we tried individual viewpoint distributions on the same 8 motifs. Only viewpoints selected for the pitch predicting system were investigated, considering the enormous number that could have been tried. The viewpoint found best able to distinguish between acceptable and unacceptable motifs was interval linked within scale. The unsuitable motifs had highest H of 5.95 and 7.25 bits, corresponding to the offending D sharps, whereas those for the suitable motifs ranged from 2.81 to 5.39 bits. It was encouraging to see these non-overlapping ranges, but a much larger sample was required to be confident of the efficacy of information content based on interval linked within scale. A further 112 motifs of 10 to 14 notes were generated to bring the total sample to 120. The motifs had various keys and time signatures. As we can see, the normal ranges of highest H for suitable and unsuitable motifs are still non-overlapping, which is what we want. Of the 120 motifs, only 5, K to O, couldn't be successfully classified as suitable or unsuitable. 92 motifs were correctly classified as suitable, and 23 correctly classified as unsuitable. So far, all of the models have used statistics gathered from the corpus. These are known as long-term models. But we can also make use of short-term models based on statistics from individual motifs as they are being generated. We thought it possible that a short-term model comprising the single viewpoint pitch could act as a filter for overly repetitive motifs by assigning them very low mean information contents. We generated a further 24 motifs for each of lengths 4 to 9 notes. Then we arranged the motifs in each set of 4 to 14 notes in order of mean information content, based on short-term distributions for viewpoint pitch only. In each case, we selected 2 adjacent motifs as being on either side of acceptability from the point of view of repetition. For the 4-note set, the boundary was placed between motifs T and U, which had mean information contents of 3.28 bits per note and 4.54 bits per note, respectively. We plotted these values as definitely reject and definitely retain, and then a regression curve was added for midway points. The curve passes between definitely reject and definitely retain, except in the case of the 9-note subject. This curve can be implemented in software as a hard boundary between retention and rejection. This is only a coarse filter, however. Some repetitive motifs occur above the line, such as a 7-note one containing 5 Ds, 4 of which appear consecutively at the end. To sum up, we've shown that a generate and test approach using multiple viewpoint systems can create suitable subjects for pieces in the style of Bach's 2-part inventions. Modifying random sampling with carefully chosen probability thresholds means that a lot of unsuitable motifs are never generated, while at the same time allowing the creation of a huge variety of motifs. Information theoretic techniques are then able to filter out a fair proportion of remaining unsuitable motifs. Interval linked within scale highest information content using a long-term model is a good way of filtering out motifs containing notes that are not within the specified scale, while pitch mean information content using a short-term model can identify some repetitive motifs. Thank you.
Thank you, Ray. So some questions here. There's one from Roger Dean. Have you tried the impact of a longer term LTM, such as appropriate earlier music, on these evaluations? It could be stylistically interesting or useful.
Not yet, no. What we've actually done so far is fairly preliminary, I suppose. We've only used a couple of bars at the beginning of each invention, so it's very style specific to the inventions, and also just a short excerpt at the beginning of the bar. So we haven't done anything as Roger has suggested yet, but certainly it would be interesting to try that. Yes.
Thank you. Question from Valeria Velardo. How did you decide for each motif whether it was suitable or unsuitable?
That was really down to my own judgment. In the case of pitch, because the subjects are certainly the first appearance of them is certainly within the scale of the key of the piece, then it is fairly obvious to try and avoid out of scale pitches, and also things like very large leaps, which in fact also I would think interval times in scale would identify. We didn't actually find that, but that may be because the probability thresholds we used got rid of those intervals anyway.
Can that not lead to some kind of circularity in your methodology?
In what way? Sorry.
Well, that basically because it's, well, that you could basically because it's only down to one person's judgment, then and you have your own conceptions about what is a suitable and unsuitable motif. How do we have some kind of guarantee that this has some kind of general applicability? Whether, I mean, there are various ways in which there are lots of motifs that Bach uses, for example, that are, if you just hear them on their own, they sound weird. They may even have many repetitive notes in them. Some of them are very long, some of them are very short. There's a lot of variation in Bach's subject style.
I agree, yes.
But what determines whether it's suitable is whether it can actually be used to create a good, complete piece of music. You can't really do that, can you? Just by looking at the subject, you know, it has to have a certain harmonic structure and so on, so you can get nice contrapuntal effects and this kind of thing. How do you get all of that just by looking at it?
Absolutely. Well, I think we allow through as I say, a great variety, and so in the end, whether or not something is really suitable or not is up to the person that's using the software. I think we let through sufficient variety for someone to make that sort of choice. I don't think we're being too prescriptive about what's not suitable. It's fairly obviously not suitable stuff that we're getting rid of.
Could you perhaps just quickly tell us this in-scale feature? What is that exactly? How is that computed?
It just gives a true, for example, in the major scale, if a particular note is within the scale of the piece.
But
so
the
it's fairly straightforward.
pieces aren't generally in scales, they're in keys, and keys contain all possible pitches arranged into a hierarchy.
Yeah, well, that's how we've done it.
Okay.
It is within the scale, and so in actual fact, whereas major is reasonably straightforward, minor is not so straightforward, because there's a harmonic scale and a melodic scale.
Yeah.
And at the moment, the in scale is only based on harmonic scale, basically
Harmonic
because a lot
minor
of my
and
earlier work
diatonic
was
major,
based
yeah.
on
Okay.
was based on harmony.
One more question here. Do you think this approach can be used to generate music with a larger structure? For example, expanding developing motifs?
Yes, that is the idea, and this is basically just the beginning of what we hope to do at some point. Lawrence Dreyfus has indicated a way that Bach may have worked in producing, well, first of all, this sort of subject, and then incorporating this subject into a smaller scale invention of a few bars, and then transforming those bars in various ways, like inverting the music and so on, and laying out these various transformations and repetitions along a timeline, as it were, to form the backbone of a piece. And then it's a case of filling in the gaps, which hopefully, again, sampling from statistical models might be a way of doing that.
Cool. Is that his book? Was it Patterns of Invention?
That's correct.
Described in, yeah. Okay. Okay. I don't think there are any more questions here in the Slack. So thank you again, Ray, for interesting talk. Thank you.
Thank you. Thanks very much.
Next is Jacopo de Berardinis. I hope I pronounced that properly. Samuel Barrett, Angelo Cangelosi, and Eduardo Coutinho, modeling long and short-term structure in symbolic music with attention and recurrence. And I think I saw Jacopo's in there.
I will cue the video.
Okay.
Hi everyone, I'm Jacopo, and together with Sam, we are going to present our work on modeling short and long-term structure in symbolic music with attention and recurrence. Let's start with a quote from the great Stravinsky, highlighting the fundamental importance of structure in music. So, musical ideas are thoroughly organized in time by composers according to a well-defined structure, which is set to bring balance between chaos and order. Not too much order, otherwise the composition will be boring and excessively predictable. Indeed, the level of structure involved in music and the degree of change within and between levels, the complexity of a piece, are fundamental for its enjoyment. This interplay between structural complexity and enjoyment has been demonstrated to follow an inverted U trend, with maximal enjoyment being elicited when melodies occur in the middle of the range of melodic originality. So what does music structure look like? In Western tonal music, music structure is said to be organized hierarchically, with musical ideas introduced, varied, repeated, and contrasted at different time scales, from rhythmic cells to motifs, phrases, and sections, depending on the specific genre or musical style considered. Unfortunately, music generated by neural networks models does not fully capture the richness and the complexity of structure in real music. However, as human composers work with interrelations among local and global structures, we would like generative systems to imitate similar capabilities. To understand where this problem stems from, we need to take a step back and consider the task on which automatic composition systems are usually trained on, that is, music modeling. Music modeling is a specific instance of the sequence modeling problem, just with musical events rather than arbitrary tokens. More generally, sequence modeling refers to the general task of learning to predict the next event in a sequence, given the historical context of the previous events. By sampling from the distribution that the model has learned, we can generate continuation of the input sequences, one event at a time. A model capable of capturing the underlying distribution to which the sequential data is subject is a powerful computational tool enabling several tasks in machine learning. For instance, improving the performance of a music model would not just benefit music generation, but also impact on several tasks in music information retrieval, such as automatic music transcription and style transfer. This is analogous to the language modeling problem for the field of natural language processing. From a technical perspective, music is more complex than text, and this is why modeling music is not so trivial. Coming back to the original problem, learning musical structure at all the possible timescales, thus encoding the repetition and the variation of musical ideas, is already there with monophonic music. Modeling music becomes progressively harder on polyphonic melodies and multitrack music. This introduced the challenges of learn bidirectional dependencies across time and simultaneous notes, and three-directional dependencies across time, note simultaneities, and voice, respectively. In this work, we focus on the problem of learning musical structure, as it is one of the major open issues currently jeopardizing the application of music models for automatic composition. In fact, a model that cannot learn musical structure will not be able to generate structured music. To sum up, given a sequence of past music events, notes, temporal slices of notes, grouping of notes, depending on the granularity of the chosen representation, our music model needs to predict or generate the next music event in the sequence. Considering the nature of the problem, our model can be highly Markov model. However, they will require an explosive number of states to repeat arbitrary patterns. Or maybe a recurrent neural network, such as an LSTM. Although recurrent networks have been extensively used in music modeling, they struggle to learn long-term dependencies, meaning that their generation tend to be either too repetitive or too contrasting after a while. And what about transformer? Well, they're currently the state-of-the-art in music modeling, but they still suffer from several problems. In particular, they struggle to learn local structure, and they do not possess an inductive bias, that is a tendency to learn iterative or recursive transformation, which instead recurrent networks do. Transformers also have resolution problems and complexity issues with long sequences. To the best of our knowledge, two approaches are mostly used to improve a model's ability to learn musical structure. Conditioning on structural cues, such as the music events at potential structural boundaries, and increasing the complexity of a model by stacking additional recurrent layers or increasing the number of memory cells. Instead of considering recurrent networks and transformers as two contenders in the music modeling game, our approach is based on the hypothesis that self-attention, the strength of transformers, is crucial for learning long-term structures. Recurrence addresses several limitations of transformer, such as learning local structures, and inductive biases facilitate the integration of both these modeling paradigms whilst optimizing the use of parameters. Our architecture incorporates all these mechanisms and provides self-attention at a linear cost, which allows processing entire musical pieces, a crucial requirement for learning music structure at all the possible timescales. Sam will now explain our architecture in more detail.
Hi, so to describe our architecture in detail, I'll do this step by step by addressing each of the problems that Jacopo has discussed already. So to start with, there are two neural network architecture types, current neural networks and transformers that form parts of our model. So RNNs are already widely used, both for natural language and music, but as mentioned, they have problems learning very long-term dependencies. So instead, we'll begin our discussion of the architecture by looking at the transformer, which lies at the heart of our architecture. So So these were introduced in 2018 and have quickly become incredibly popular in natural language processing and are gradually replacing recurrent models in many contexts. So for example, the GPT models are transformer based, but there has been some success in applying these to music generation as well. So instead of processing a sequence note by note like an RNN would, transformers share information by looking at pairs of notes. So this is called the softmax attention mechanism. So each note, it has learned how much a note cares about other notes in the sequence, and propagating information across a sequence only takes one step to do, no matter how far away the two notes are. Whereas with a recurrent neural network, to propagate information, it's got to travel back all the way through the sequence. So as a result, this means transformers have a capacity to learn much longer range connections. However, unfortunately, the computational complexity of performing this operation for the vanilla transformer is quadratic in the sequence length, which is prohibitive for the kind of length sequences we want to consider. So to solve the complexity issues, very recent developments in transformer architectures have introduced a new kind of attention, which is in fact linear in the sequence length. So this is really good news because it means we can throw really long sequences at a transformer model and it can cope with them without requiring a supercomputer to do so. So on a high level, this is done by defining the attention between each pair of notes as a kind of multiplication, a kind of dot product between vectors. And this allows a neat factorization, which allows reuse of computation between all of the sequence positions. So the details of how this is done is in the appendix of our paper. So the next problem to solve is the inductive bias problem. So to do this, we incorporated aspects of a kind of transformer called the universal transformer. So this differs from how you normally use transformers in that instead of having a stack of transformer layers as you normally do, you have a single transformer layer which has a recurrent connection to itself. So this is a recurrence in depth, not a recurrence in time. So in effect, this is just a weight sharing across a stack of transformer layers. However, the original universal transformer paper used softmax attention, whereas ours uses the linear attention mentioned before. So combining these two isn't a problem. So finally, to solve the resolution issues with transformers, we introduced some recurrent neural networks to the mix. So the resolution issues are caused by the explicit positional encoding in a transformer. So without a positional encoding, the transformer has no notion of time. It's basically operating on an unordered set of data unless you tell it when each part of the sequence occurs. So by adding an LSTM to the input, this removes the need.
It seems like the conversion failed at that point. Let me share my screen and then run that code.
Conversion failed at that point. Let me share my screen and then
Okay. 1 second.
Some time. So in effect, this is just a weight sharing across a stack of transformer layers. However, the original universal transformer paper used softmax attention, whereas ours uses the linear attention mentioned before. So combining these two isn't a problem. So finally, to solve the resolution issues with transformers, we introduced some recurrent neural networks to the mix. So the resolution issues are caused by the explicit positional encoding in a transformer. So without a positional encoding, the transformer has no notion of time. It's basically operating on an unordered set of data unless you tell it when each part of the sequence occurs. So by adding an LSTM to the input, this removes the need for an explicit positional encoding in favor of a learned positional encoding. And it also has other benefits like helping to locally contextualize the music, for example, learning a representation of what chords are active, what notes are currently pressed. And we also added an LSTM to the output side of the architecture as well. So this helps reconstruct this data because it might be difficult to do so locally. So for example, if the model decides to press to begin a note, it needs to remember to unpress that note after a specific amount of time. And this is something that requires local knowledge as opposed to global structural knowledge. So intuitively, if this was a natural language model instead of a music model, this would be equivalent to remembering to close your brackets and that kind of thing. And LSTMs, we know, are pretty good at learning precise timings as well, whereas transformers aren't quite so good. So we have now arrived at our full architecture.
Based on our hypothesis, we evaluated our method on the music modeling task and compare its performance to a vanilla LSTM, an attention LSTM, a transformer, and a universal transformer. To train and evaluate our model, we chose a dataset of long and structurally complex musical pieces, the Maestro collection. The dataset collects more than 1,000 classical piano performances in MIDI format, which we quantize to the 16th note and transpose to all keys to learn transposition invariant features. To circumvent the problem of learning note simultaneities, chords are unrolled in time and so represented as arpeggios. We do not trim nor discard our music sequences, as we want to study our models on entire music pieces, thereby testing their ability to learn structural properties of music. Models are evaluated on the test set based on the cross-entropy laws, measuring the distance between the target distribution, the actual music sequences, and the predicted one. In line with our hypothesis, we found that the use of attention improved the modeling performance of the vanilla LSTM, although the transformer-based networks are still better at predicting music. The small improvements of the transformer over the universal transformer is not statistically significant, meaning that universal transformers can achieve the same performance with half the parameters. Finally, the LSTUT achieved the best performance on the Maestro dataset. To analyze the ability of the LSTUT to learn music structure features, we inspected the attention distribution of the attention heads and compared them to the self-similarity matrices computed on the same music. Self-similarity matrices are extensively used in music structure analysis. To compute one of them, all elements of a music sequence are compared with each other for similarity. When visualizing such matrices, repetitions typically yield path-like structures, whereas homogeneous regions yield block-like structures. As an example, we chose Fly, a minimalist composition for piano, exhibiting both local and global structures. This is particularly evident after inspecting the piano roll reported above, as well as from its self-similarity matrix below. As you can see, the attention distribution of this selected attention head on Fly is not so different from the self-similarity matrix, especially if we note the block-like structures of different size emerging from both this visualization. This observation supports the fact that the LSTUT can learn structural features at different temporal resolution, even if the model has never seen a minimalist piece in the training set. So the takeaway message of our presentation is that you should use a universal transformer, if possible. Consider entire tracks to learn musical structure at all possible time scales, and combine self-attention with recurrence to take the best of both worlds. It is now time to start generating some structured music with our model. And to provide a more comprehensive study to the field, we are now conducting an extending experiment to compare multiple architecture for music modeling and different representation of symbolic music to analyze their impact on learning structural features at different time scales and on different datasets. Another promising direction that we are investigating is the alignment of attention heads with self-similarity matrices for promoting their specialization, structurally speaking, and increasing the interpretability of our models. Thank you for your attention and stay tuned for future developments.
Okay, we've returned.
Okay, do you want to give me a highlight? How do I get that? Bob, do you want to give me a highlight?
Yes, I've given it to you.
You have. Okay. Why can't I see it? Oh, there we are. Okay. Thank you for that talk. Are there any questions in Slack? I'm just checking here. So what have we got? No questions yet, apparently. Okay. I have a quick question to while people are thinking. So you were comparing the self-similarity matrix with the attention. The map of the attention there, and showing some that there was some kind of correspondence between them. Clearly, the self-similarity matrix depends entirely on how you measure the similarity. So how were you measuring similarity there?
Thank you, David. So basically, we measure the similarity with the cosine similarity on the feature vectors extracted by basically synthesizing the music piece. This is not extremely elegant from a critical point of view, but I mean, in future work, we would like to explore more the use of self-similarity matrices computed on symbolic music. There's a lot of work on computing self-similarity matrices from symbolic music, but it's a bit not organized at the moment. So it would be nice to rediscover these approaches and to revisit these approaches and bring them in the context of music generation as well.
Okay, thank you. There's a question here from Valerio. Did you run a user study to evaluate the generated results?
Not for the moment. I mean, we focused on music modeling for this work, and we are now working on the generation of our model. We found that when there are multiple goals to achieve, when there are multiple properties of music to learn, the model might be confused. So we might get a model which is extremely specialized in learning musical structure, but at the same time is not getting other properties of music. So there is still some, let's say, there is an open gap between modeling music and generating music, and we are actually working on that at the moment. And then we will be able to run user experiments, and we are also considering the use of some structural measures, some measures of structural complexity that we managed to implement, and we will ideally be able to automate this process computationally. Rather than running user experiments, we can just generate some music from our models and compute these measures of structural complexity.
Mm-hmm. Thank you. There's the next question, which is, can we listen to an example? I don't think we have time right now, but can you give us a link to some examples that are generated?
Yes, not right now, but yeah, I need to upload some of the generation, and then I will provide all the links.
Yeah, that'd be great if you could put the links into the Slack discussion for your paper. That would be great if you could do that.
Absolutely.
Thank you.
Thank you so much, David.
Sorry?
Thank you thank you a lot, David.
Okay, I haven't quite finished. There's a couple of more questions here.
Oh, good.
Robert Laidlow asks, as a tool for composers, might it be possible in the future to, one, create a structural skeleton without fine detail, so that's specific, without specific motivic material or pitch material that a composer can fill in themselves? Maybe that could answer that first.
Yeah, hi, Robert. Thank you for your question. It's very interesting. So there are some works out there basically focused on generating the structural template of a piece and then filling like this template. I remember like a couple of works from Izmir last year, and they were actually training generative adversarial neural network to generate self-similarity matrices as images. And then from these self-similarity matrices, you can actually have a template to fill for a generation. I'm not sure if this, I mean, I haven't checked personally the generation obtained from these models, but this is actually a nice direction that we also like to investigate in our work, like separating.
Yep. Second, he asks, have you considered using different music generating model to create the material that your model structures?
Sorry, David, how do I use?
So the second question from Robert was, have you considered using a different music generating model? I think what he means is like on a local scale to create the material that your model structures.
So in principle, our approach doesn't need another model to process the input sequences. It's like the combination of the recurrent networks with the transformers should already achieve this. But regarding the combination of different models for music generation, I think one of the nicest work out there is the work from Hannah Wang, which is invited to the conference as well. And she was also presenting last week at Izmir. And she basically, she ran a large experiment with different groups investigating how different tools, how different models for music generation can be combined together and used by real artists, basically.
Okay. So I might be able to add to that, actually. TensorFlow, which is what we programmed this in, makes it easy enough to switch in the LSTM for any other model which is differentiable. So as long as it can be trained with gradient descent, it can be plugged into either side of the transformer, and it should in theory just work. But we only experimented with LSTMs and didn't look at GRUs or anything like that.
Okay.
Thank you, Sam.
Thank you. Final question. Rui Guo asks, Ray asks, is it similar to Transformer XL? The LSTM is used as a first layer. Does it still suffer the issues of LSTM for long sequence modeling?
Yeah, so I'm not familiar with Transformer XL, but for the second question, so yeah, the LSTM you might think still has problems learning these such long sequences, but because the transformer can kind of route the gradient propagation across the whole sequence, at least the LSTM on the input side shouldn't suffer from that problem, because to backpropagate gradient to the start of the sequence, you can just go straight via the transformer to get that.
And the final question from Ray, will the code be open sourced?
So yeah, we are going to open source the code, but yeah, first we need to complete our experiment, and yeah, then we will reorganize the code, put everything in a repository, and release it.
Okay. Thank you very much, guys. I think we need to move on now to our next talk.
Thank you.
Thanks for a nice talk. So the next one is a work in progress by Aiko Uemura and Tetsuro Kitahara with the title Morphing-Based Reharmonization Using LSTM VAE. Yes, over to you, Aiko. If you are there.
Thank you, David. Can you hear me? Yes. I'm Aiko Uemura from Nihon University, Japan. Today, I'd like to talk about reharmonization model using LSTM, VAE, and melody condition. Let's start with background. Reharmonization is a technique of replacing the original chord with another chord without changing the melody. For example, please listen to these songs. We have a different impression of these songs, but the melody is the same. However, it's not easy for beginner musicians. Its automation can enable us to enjoy playing songs in various styles. So what is so difficult about reharmonization? it's controlling the style of generated code progressions. The controller should be intuitive and musically understandable. Also, it should be user-friendly for people with no musical knowledge. So we focused on morphing in a latent space as a controller for reharmonization. Morphing is a technique of generating the media data between two given instances. Several studies of morphing have been presented. They treated with melody, chords, drums, and bass. The most famous is music PA, you know. Others like MIDI PA dealt with styles. The VAE-based methods focus on the interpretation of latent space, so we followed this idea. On the other hand, they weren't considered with the constraint of melody identity. Therefore, we examine morphing in a latent space as a controller for reharmonization. Our old study proposed a PAE approach. However, code progressions tend to switch instead of changing gradually because we didn't consider the time series in the model. We improved this using LSTM BAE and melody condition. We consider the temporal connection. Also, we incorporate the constraint that the melody is identical in reharmonization. This figure shows our network structure. It has LSTM encoder and decoder. All of them have a bidirectional structure, and the hidden size is 128. The latent variable Z has 64 dimensions. We treat 4 octaves and use the data of 4 bars. The number of notes contained in a chord is limited to 5. And one note is represented as a one-hot vector. We deal the melodic pattern as a condition. We compared our old model. It was a simple BAE. It has 2 layers of MLP in encoder and decoder. The hidden layer dimension corresponds to the 128 dimensional model of 16 sequences of LSTM cells. Here, the experimental conditions that code progressions include common pattern data from music books and manually reharmonized chords by a professional musician. We split notes longer than quarter notes. Also, our music is transposed to C key. The parameters for learning are as follows. We conducted morphing between Z1 and Z2 using this formula. Z1 and Z2 are latent variable of 2 songs. They are Japanese children's songs, 明日の明日のまた明日. And Z2 is Then I'll show the result. These pictures show PA results. When alpha is 0, it should be close to Z1. And when it's alpha is 1, it should be close to Z2. Oh, as you can see, the reconstruction was failed. The VA morphing result alpha equal 0.5. The results show dissonant or unnatural chords, especially in the second and third verse. Well, these are LSTM-BA results, which so alpha is 0. And alpha is 1. Well, we can see the reconstruction results were better than the VAE, and moving results LSTM allowed more consideration of chord connections than the VAE morphing. In addition, we checked the effect of melody condition. We kept the chord progression and chroma features intact. We changed the melody condition of 明日の明日のまた明日 to the water is white condition. When we put simple arrangement, and after changing condition, as you can see, bass note changed slightly. It's simple chord progression. Next, we used chords including 7th and 9th notes. After changing the condition, we found that the chord progression was converted into one that consists of 7th, 9th, and tension notes. The decoded result fit the melody and reflected the component notes of the input chord progressions. Let me summarize my talk. Our experimental results show an LSTM VAE has a higher reconstructed quality than a VAE. Also, we confirmed effect of changing the melody condition. We found that generated chord progression fit the melody and reflected the style of the input. Thank you for your attention.
Thank you, Aiko.
Thank you.
Any questions here in I think we have time for one or two questions. So I would just like to ask you, so in your conclusion there on that slide, you say that the LSTM VAE has a higher reconstructed quality than a VAE.
Yes.
How exactly do you come to that conclusion?
Oh, sorry?
How did you come to the conclusion that one is higher quality than the other? I mean, most of these chord progressions are very simple and stylistically very neutral, apart from the ones that aren't. And but I mean, what's better about? How do you make that evaluation?
Oh, it's under progress, so we didn't evaluate it by by experiment.
Okay.
So,
but I mean, I'm not even sure how you would do it by experiment, but
so we have to check the result and evaluate it.
Okay. And your other conclusion was, could you just go back to your last slide? Generated chord progression fits the melody. So whether or not a chord progression fits the melody is stylistically dependent. So some chord progressions would consider to fit a melody within one style, but not in a completely different style. And the whole point of this is about reharmonization, where you take something from one style to another, and presumably to evaluate that, you need to have some conception of what those styles were before you actually do it, so you know what you're trying to target for. But there's no indication here of what the styles are that you're moving from and to.
Yeah, as I agree with you. I think it's close to a style change. And what I'm interested in is the difference of the sounds of the chord progressions only. So in this study, I focused on the chords only, and because rhythm itself can change the impression.
But couldn't you do that basically with like any kind of model? Why is the, again, it comes back to, you know, why this model rather than another model? And clearly you need to do some kind of evaluation to make those claims, don't you?
Yes, I agree with you. Sorry, could you say that again, please?
Sorry?
Sorry. So is your
I'm just asking why this model? Why would I want to choose to use this model rather than another model?
Yes, I use this model because we like to deal with time series, and it's important for chord progression to use the time series. So LSTM is suitable for dealing with time node connection.
Okay. Yeah. Okay. Well, thank you very much, Aiko, for an interesting talk.
Thank you so much.
Yep. Thank you. Our last talk in this session is a demo by Richard Savory, Lisa Zare, and Gil Weinberg. Are you guys ready to present that?
Yes.
You are. Then I guess it's over to you.
All right. Go. Cool. So hi, everyone. I'm Lisa, and I'm going to be talking today about emotional musical prosody. So our validated vocal data set for human-robot interaction. And Richard Savory is also here to help answer questions at the end. So as an introduction, our motivation for this is that communication between humans and robots is of increasing importance. And many such systems rely on speech, but semantic meaning for these communications isn't always required or even necessarily the best choice. And so we were investigating an alternative of non-linguistic musical prosody to facilitate this communication. So prosody is essentially intonation and rhythmic aspects of speech. It's how you might be able to tell if someone's being sarcastic when they say something, or if they're saying something in a happy tone or a sad tone. This musical prosody has been shown to increase trust between humans and robots, and it may help to avoid the uncanny valley where robots become so close to a human that they become a little bit creepy. So we created a custom data set of emotional musical phrases. For our emotion model, we used the Geneva emotion wheel, which is pictured on the right. It has 20 different emotions arranged in a circle. And one of the reasons we liked this model to use was that each quadrant corresponds to a different valence arousal pair. So for example, the top right quadrant is high arousal and high valence emotions. When we were creating the data set, we had one female singer improvise phrases 15 minutes on each emotion. where each phrase was 1 to 15 seconds long. We manually split up the phrases, and once we eliminated silences, this resulted in 4.2 hours of data for an average of 122 phrases for each emotion. While we only had one singer for this, which in some ways is a bit limiting in that we only had one interpretation of the emotions, for the purposes of generation, we find it actually has some benefits in that it makes the data set consistent in terms of having one interpretation of each emotion in order to train on. So I'm going to play some examples from the data set. Hopefully you can hear these. I have one for each of the different valence arousal quadrants. Okay, this is anger. So I picked some of the shorter ones for the purposes of demonstration. But as you can hear, there are quite a few types of differences between these phrases. There's pitches, different rhythms, different volumes, different timbre in the singer's voice. But we primarily, for this paper, focused just on pitch. So we converted each of the phrases to MIDI using the CRAPE algorithm for pitch detection, and then writing an onset detection function largely based on the confidence values that CRAPE outputs for how confident it is that each thing is a note, and then applying a median filter for smoothing, as well as looking at pitch derivatives and some other onset detection functions. And then we tuned this data using just a histogram of pitch deviations. Since she was improvising, it was possible that she would go out of tune during the course of the session. So this was just to make sure it was converted correctly to MIDI. And on the right is just some features that we found a little bit interesting about the data set. So if you look at the x-axis, this is the average pitch amount, so how high the pitch was. And the higher valence emotions, so the happy and calm, overall had higher average pitch than the lower valence ones. On the y-axis, we have plotted average note length. So what we notice here is that the higher arousal emotions actually have shorter notes on average. So if we compare anger to sadness, for example, the anger category has shorter notes. We also trained a vanilla VAE on our data. So without telling the VAE any information about the emotion, we just trained it on pitch alone. And plotted here is the latent space of the data. We've reduced it from 100 dimensions to 2. And even though it had no knowledge of the emotions, from the colors, you can see that it actually kind of has plotted these emotions in different parts of the latent space, showing that it is learning something about how each of these emotions represents the pitch differently. For our validation of the data set, we had an experiment with 45 participants using Mechanical Turk and Prolific. And we gave each participant randomized 60 questions from 3 different categories of question. So the first category was the best category, where we manually selected 5 phrases for each emotion that we felt well represented that emotion. This was primarily for the purpose of having several phrases that we could have validated and say, this phrase is joy, we have validated it specifically, we know that it works well, it's easily identifiable. But we also had an all category where this randomly selected one phrase from anywhere in the data set to give a better idea of the data set as a whole. And then we also had attention check questions randomly come up, which was just audio telling the participant to select a certain emotion so that we could eliminate participants who weren't actually paying attention to the study while doing it. And down here is a plot or a table where I've combined the best and all percentages and statistics. So looking at the percent in correct quadrant, this is how many people identified the emotion to the correct quadrant. So overall, it's over 50% for most of the quadrants, except for this last category, calm, where it's a little bit below. We then also have average distance plotted. So that is how many emotions off they were on the wheel on average. And what we noticed is that these 2 at the bottom are the highest, and those also correspond to the lowest arousal emotions, so the ones with the less energy, which sort of implies that if an emotion has less energy, it's a little bit harder to tell which emotion it is, which does make sense. And this also matches up with the variance, where these 2 quadrants had the highest variance. We then used a VAE conditioned on emotion in order to generate some phrases and to create the audio. So the VAE, it's a convolutional VAE, and it outputs just pitch, so we convert that to MIDI. And then we sampled notes of the singer. We had her sing chromatic scales on different emotions, and we've just sampled those to create the actual audio output from the VAE. And then we validated this data set using the same setup as the data set validation. So I'll play you these examples from the generations. And then we also have plotted here the raw output from the validation experiments. So these are rows plots, and we've just combined it for each quadrant. So we would expect to see most of the results ideally in the correct quadrant. So quadrant 1 in the upper right, quadrant 2 in the upper left, and so on. And just kind of looking at this, you can see that overall that did occur, maybe with the exception of quadrant 4 here for the generated, where it's a bit spread out. There are some quadrants like quadrant 2 where the generated is more spread out than the data set, but overall things were, for the most part, in the correct quadrant. For future work, we plan to do a lot of different studies using generated prosody and applying it to HRI. Some specific ideas are to vary group sizes, so have groups of humans interact with a robot, groups of humans interact with groups of robots, those types of combinations, and also to look at robots with different personalities and see if we can represent different personalities using this generated prosody data set. So thank you so much. And if there are any questions?
Thank you very much, Lisa. Any questions in the Slack? I have a quick one for you while people are thinking. Which one shall I ask first? This one. The 2 dimensions in the reduction there. Do you have any idea what they are, or how they can be interpreted? These dimensions, or are they just something that's some extremely? What can you tell us about these 2 dimensions? What do we actually learn from this? How is the model trying to do this classification?
Yeah, I can answer that one. That unfortunately we don't really know much from this at the moment. So that's the next stage of our research, to try and work out what this means exactly. But really, this is just a reduction. It's just like a TSNE. We tried to do a dimension reduction. So we can't actually learn from this. All we can learn is that the way the network understands the input is that it groups these things together in terms of pitch. So yeah, it's not a great,
No, but you know that a model can find 2 dimensions that can fairly, to some extent, separate these classes, but we don't know what those dimensions are.
Yeah, for sure. So we don't actually know the specifics, but we do know that it can learn, which was really, so this was a concern for us, that it would just not group them at all, or not learn, separate them. No. So seeing these results was actually really positive for us.
Yeah, it gives some validation to at least the reality of the classes.
Yeah, for sure.
Yeah. One other question, I'm still waiting for questions in the thing here. You choose to use MIDI rather than audio, so you lose all the microstructure in the examples, but presumably it is using that microstructure to do the classification here, right? Or is the classification done only on the MIDI?
Yeah, so this particular one was just MIDI actually. But yeah, the whole point of recording the singer was to use all the timbre and all that stuff later on. So yeah, we just wanted to focus just in this little demo now on the idea of pitch and see if we could capture from pitch. But we're definitely working on using audio samples for generation as well in the next stage. So we also classify
pitch. One would imagine that it's the microstructure in the pitch structure and you can actually hear that also, right, in the generated examples. I mean, as humans, we listen to that and we don't hear any emotion in them because the microstructure's gone altogether, but your model has presumably learned some learnable features, some regularity in just the information that's preserved in the MIDI data. So to do with quantized rhythm and pitch.
Yeah, so actually, I think MIDI might be the wrong word in a way because it's not really MIDI. It's like MIDI frequencies, but it's sampled every 10 milliseconds and it's just a constant stream. So it does actually sort of include vibrato and things like that to a degree.
but the pitch is quantized, right?
It's not, no.
The pitch isn't quantized either.
Yeah, no.
Oh, right. Okay.
Yeah, so it's very loosely MIDI.
Okay, right. Okay.
Yeah, so sorry, MIDI might be the wrong word in a way.
Okay. Fine. So it's like super resolution MIDI with.
Yeah. So you can detect vibrato and all that stuff in it, and it's like super micro timing as well.
Oh, okay. Then why isn't that coming out in the generated examples?
Yeah, so the problem with the generated examples is that we have this disconnect from the way we produce the sound at the moment. So at the moment, it's like a audio sampler in a way. It plays back. And so, yeah, that's the next stage, to work out a better way to actually play it and connect it to tempo.
Finally got a question here from Ray. Does the choice of emotion wheel help to explain the factors of emotion? For example, pitch and rhythm, he asks.
Factors of emotion.
I'm not quite sure what he means by that, but maybe you are.
I'm not quite sure what the factors of emotion means.
Does the choice of emotion wheel help to explain? Ray, could you perhaps fill out your question just a little bit?
Maybe Lisa knows what that means, but I'm not exactly
I'm not sure either. Part of it might be there might be similarities for closer emotions. And one good thing about the wheel is that there's kind of like this idea of neighboring emotions, and you can tell sort of one emotion how far apart it is from another. I'm not sure though if that's related to his question.
He's written valence more with pitch, arousal with short rhythm.
Okay. Yeah, so the wheel, definitely the valence arousal, we think is related to these features. We were just plotting here kind of two that we found that were interesting, where it was very easy to see the separation. So this is just two examples of features. There are, I'm sure, many more that you could run on pitch, and we're still analyzing this data set. But yeah, the wheel definitely with the valence and arousal helps to separate those out.
Thank you very much, guys. I think we have to stop there because the session ended 6 minutes ago officially. But thank you for a very interesting session to all the presenters. And I think some claps are definitely in order here. So thank you very much for